Mathematicians, we're checking out the chain rule. And chain rule is like a little bit deeper analysis of how to take the derivative of something that's not in perfect shape like that. If we were going to take the derivative of that, the derivative would look like that, right? You'd say this times this, you'd multiply those together, there's the 18, and then you drop the exponent by 1, hence the 1, and you do the same thing here. 1 times the 6 gives you the 6, and then this would be x to the 0, which is just a 1, so we cancel that out, or we ignore that, and then the derivative of a 1 is just a derivative of a flat line at 1, if I draw it right. There you go. What's the slope of that thing? 0, so that thing's out, right? So there's our derivative that we'd expect. Now, a twist comes in if that original equation looked different. They are the same, right? Like if you expand this, you get 3x plus 1 times itself, and 3x plus 1 times itself, right? And if you multiply these together, there's your 9x squared. Here's 3x and 3 more x, 6 x's, and there's the 1. So these two are equivalent, right? Why I'm asking you right, you can't talk back. So the problem comes if you take the derivative of this, which we're pretty confident in, we get this. And if we take the exact same thing with slightly different look, and we just kind of like guess at how to take the derivative, it might look like this. You might say, let's take the derivative, multiply the 2 in front of all this mess, and then drop this by 1. Fine, good enough, right? And if we distribute this in, this is 6 and 2, but that's not right? We're off, and we're off by, well, let's see. I'm supposed to get 18x plus 6. Instead of 18 x's, I have only 6 x's, and instead of 6, I'm getting 2. So to me, it looks like we're off by a factor of 3. Do you see that anywhere? So that's what we're going to deal with, is looking at how to, instead of expanding this to this and then take the derivative, how do we take the derivative of something that's kind of buried inside, things that are like operations that are chained together. So the chain rule works when you have a little function buried in another function. So here, the function is blah, blah, blah to the 4th. That's the outer function. And the inner function is x squared minus 2x. Ba-bam, ba-bam, ba-bam. So inner function is, oh, I wrote them backwards. Thanks, very helpful, Gorkevich. The inner function is this blue inner function here, and the red outer function is the x, to whatever you put into the 4th. So there's a function buried within another function. Here's another example of a function buried in another function. Maybe it's a little bit harder to see here, but maybe if we switched it to this, if we thought about this as, well, maybe like this. There's an equivalent. 4 times all of this stuff. The 1/2 is from the radical, and the negative is from being in the denominator. So here is maybe a more approachable way to look at this function. One of the outside piece of the function is this 4 times blah, blah, blah to the negative 1/2, and the inside is the blah, blah, blah. And what we have is f of g of x, composite functions, right? It's all blending back together. So that's what we're going to mess with a little bit. Let's check this out. If we expanded this, you don't have to do that because it's annoying, but you could. There's that, and then if you took the derivative, you'd get what, 18 and a 6, right? I'm going to re-lens that. Let's just turn it into this. I'm going to factor out a 3, just for fun. And I might also clean it up just a touch. I'm going to break this. I factored a 6 out of here, right? Here's the 6. Here's what's left over. And instead of calling it 6, I broke it into 2 and 3. Not just to be difficult, but to illustrate something. Here's this 2. And if you're just taking the derivative, you would expect to multiply the 2 out in front. Shazam. Drop that thing by 1. shazam, and then kind of be done with it. But we realize that there's something else sitting there. It's a 3. It's this coefficient, but it's really the derivative of this inside sitting here. So we took the derivative of the outside and kind of left the inside just sitting there stewing. And then later, we multiplied by the derivative of the inside. And when you clean that up a little bit, we get the derivative that we expect. What is this? So as a little illustration, here's the derivative of the outside. The red part is our outside function. I've made it like kind of off red to mean that we've changed that. We've taken the derivative, and there it is. And here's the bright blue inner function, and here's the darker blue derivative thereof. Let's try another one. Same sort of idea, expand it, it would look like that, right? All I'm doing is saying it times itself, expand. And if you took the derivative, it would look like this, 0, -4, 8, because you're going 2 times 4 and then dropping the x by 1. If we clean that up, factor out a 4, and then just, you don't have to do this, I'm just illustrating what's happening. Break that 4 up into a 2 and a -2. Well, the 2 makes sense because you would take this 2, you'd multiply out front, and then drop this by 1. So here's this, and then this, and then the inside, this piece is the derivative of the inside, which is just -2. So there it is. And so a smoother way than expanding something, because sometimes you can't, I'll show you in a second, is to take the derivative of the outside. So here's our original function. Take the derivative of the outside, right? Multiply the 2, drop this by 1, leave the inside intact. Don't mess with it. And then multiply by the derivative of the inside. And then you can smush it together or leave it and run away bravely. So again, let's try this. To the 4th, you're welcome. You didn't have to do that. And when you expand it, you're more welcome. Here it is. You could have binomial expansioned it, and I know you love that, but if you take the derivative, it looks like this. 8, 20, 48, 96, right? If you multiply the 3 and the 32 and 64. And you can still factor out an 8 and then play the game. This whole thing factors down to 1 minus 2x cubed. You're welcome, right? You wouldn't have seen that coming, but going from here to here, just wanted to show you that it works even with not perfect quadratics. So this boils down to this. And we can break that 8 up also into a 4 and a -2. So I just want to show you that this, if you were using the chain rule, you'd say this should be, well, like this. Here's the original. We'd multiply this 4 in front. We'd drop this 3 down. You'd leave the inside intact, and then you'd multiply by the derivative of the inside, -2. Voila. And lo and behold, it works. It's pretty neat. So here's the formal jargon. I love this, the way they write this. This is, if you're trying to take the derivative of y with respect to x, talking about x's, if there's a different little function, u involved, the fu function, you have to take the derivative of the outside function with respect to that inside, with the inside just sitting there. And then you take the derivative of the inside with respect to x. This is a little bit gross, like the notation. This is what's in the formula booklet. This is the notation that I use when I think of it. If I have an outside function in red, this f of x, this function, and I have an inside function in blue, you take the derivative of the outside, hence it's in kind of dark red because we've derivativized it, leaving the inside exactly like it is. And then later, in our own darn time, take the derivative of the inside and multiply them, clean it up if you can. So derivative of the outside, leaving the inside, times derivative of the inside. That's my notation that I like. Here's fancier notation. Let's try it out. Oh, maybe the hardest part. I look pretty good on there. The hardest part, I think, is sometimes recognizing this. So is this one composite? Yeah, there's the inside function is this piece, and here's the outside function. boom, squared. So yes, composite. This, not composite, it's just two things multiplied together, and we would expand it or use the product rule. Foreshadowing, bum, bum, bum. We don't know the product rule yet. This, no, there's only just x sitting there, but this is sine of 2x, right? So this has a piece outside and an inside functions. Same thing, this is sine of cosine of x. So this is composite, it has two different things. This is just sine of x times cosine of x. It's a product. We'll have to use product rule on it tomorrow. So let's try it out. Here's my outside function. So if we're trying to take the derivative, we'd multiply the 10 in front, leave the inside and drop this by 1. Leave the inside intact. And then later, at our leisure, multiply by the derivative of the inside, so negative 11. And then you could mash them both together, like if you really wanted to. All right, so you call this negative 110 to negative x to the 9. Done. Right. This one's a little bit uglier, needs a little bit more setup, but just rename it. Right. It's this. I don't know what to do with the square root. Ugh, that's the worst bracket ever. Can't undo it now. I don't know what to do with the square root. We'll get rid of it. Ignore your problems in life like normal. There's another way to say exactly that function. If you're trying to take the derivative, you're multiplying by the exponent in front. Leave the inside stuff just as it is, 4 minus 3x. I don't know why I'm changing colors now. And drop this by 1. And we're done. Oh, wait, we're not done, right? We get excited. Multiply by the derivative of the inside, which is negative 6. Cool. And then
x, the derivative has an x in it.
The derivative is negative 3x.
Add an x.
I don't think he can hear me. You know what he means. Get with it, Yurkevich. Oh, well, maybe we'll just throw some x's in there. There you go. Something like that. Cool. And then maybe if you're feeling like a superstar, it started life with a radical. It looks cool if you end it with a radical. Notice the 3 doesn't have the half on it. The half only applies to this, so the 3 is still in the numerator. The half here is the radical. The negative is the big fraction, and you got the 4 minus 3x squared. Move. So this looks fine. This is double good. Double good. All right. I think that is the ball game. Those are the overall pieces. Here's a couple of practice problems to give a shot. Here's some solutions. There's also some other stuff on the VLE as well. It says chain rule practice, extra chain rule practice. That's a little more complex. If you breeze through this and you're like, I got it. Try that other stuff because you might not. Yeah. 7's interesting, but we might not have time for it. So give those a shot, and I will see you later.